Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Welcome to my final year project presentation. I am Nur Ainsyara binti Amla, a final year student of Bachelor of Science Honors Chemistry with Management. My project title is The Effect of Simulated Body Fluid on Commercial Wollastonite Sodium Arginate Composite Cement Scaffold. I am supervised by Sir Henry Johan bin Muhammad Rizwan.
My presentation slide are cover about Chapter 1 Introduction, Chapter 2 Review of Related Literature and Studies, Chapter 3 Methodology, Chapter 4 Results and Discussion, and last but not least, Chapter 5 Conclusion and Recommendation. Wollastonite ceramides have been researched as artificial materials for artificial bonds and dental roots since the 1990s because of their high bioactivity and biocompatibility. The focus of the research is to develop an alternative approach based on biomaterials with strong bond regeneration potential that is both feasible and cost-effective with few problems. Bionic biomaterials with important qualities like biocompatibility, degradability, appropriate porosity, and mechanical strength have recently shown promise in meeting bond regeneration needs. Unfortunately, wollastonite has significant drawbacks. The first one is rapid breakdown, which raises the pH value to dangerous levels and increases the concentration of calcium ion and silicate ions. The second drawback is the lack of mechanical strength of scaffold and monolith made of wollastonite. There are two objectives for the study. Firstly, to produce wollastonite sodium alginate composite cement scaffold. The second one is to observe and analyze composite cement immersed in SPS solution by using FTIR and SEM. Biomaterials are very outstanding in the fields of tissue engineering and regenerative medicine. Wollastonite, which has the chemical formula CaSiO3, is a special substance despite its uncomplicated composition. It can be used as a filler material in ceramides, polymers, paints, concrete carbon dioxide cured binding materials. In simulated body fluids, some researchers discovered that wollastonite ceramides are bioactive and that the development of apatite on CaSiO3 ceramides. Calcium dissolved from the wollastonite coating is thought to increase the apatite's ionic activity in the SPF, causing apatite to develop on the coated surface. One type of bio-based polymer, sodium arginate, was chosen for incorporation with bioactive calcium silicate in the creation of composite scaffold in this study. Simulated body fluid is a protein-free, supersaturated calcium phosphate solution with an ionic composition similar to that human blood plasma. SPF is the most commonly used testing medium for evaluating material qualities like bioactivity and corrosion resistance in biological media. Preparation of composite cement. Firstly, the cement prepared by the ratio solid to liquid 0.5 gram per liter. The materials mixed and stirred with spatula. The mixture placed into stainless steel mold. Cements were then taken out of the mold and dried in an oven for 24 hours at 37 degrees Celsius. The weights were measured. Then, preparation of 1 liter simulated body fluid. 700 ml distilled water was added into a 1000 ml beaker with stirring bar. The beaker was set on a hot beaker plate. Non-reagents were added and dissolved one by one. Trace was gradually added until the pH reached 7.45 and the temperature sustained at the 36.5 degrees Celsius. Hydrochloric acid was then gradually added until the pH was precisely 7.40 and then soaking composite cement in SPF. Cement requires 0.1 cm² per ml of SPF to be submerged. The cement was submerged in a plastic container and placed in a water bath shaker set at 36.5 degrees Celsius for 3, 6, 9, and 12 days. Each soaked cement was replenished every 3 days. Then, the samples were submerged in the acetone solution, shaken carefully, and rinsed with distilled water 3 times. The specimen was dried for 24 hours at 60 degrees Celsius. The semen's pH measures on day 0, 3, 6, 9, and 12. Each semen before and after immersion in SPF solutions for 0, 3, 6, 9, and 12 days, weight loss was measured. And then, investigations were conducted using FTIR and SEM. FTIR used for structural examination, and SEM to get further details such as the surface morphology of specimens. The mass of the composite semen sample was weighed before and after being submerged in SPF. The average mass loss of the samples is shown below in Table 4.2 and Table 4.3. Loss of weight is caused by the dissolution of calcium silicate hydrate and other phases, as well as the amount of semen lost is more than the amount of apatite that is deposited on the surface of semens. The great ability of semen submerged in SPF solution encouraged the release of ions like calcium, magnesium, and silicon ions and their exchange with H3O+ to generate HSiO43+, which acts as a site for the nucleation of apatite. From day 3 to day 12, an electrode pH meter was used to measure the pH of semen that had been soaked in SPF solutions. The result showed in figure 4.1 that both pH levels increased from day 3 to day 12 in both samples. The pH rises as a result of the release of alkali ions into the solution as the scaffold dissolves. Based on the figure 4.2, there is no apatite formation at this phase due to the samples were not immersed in SPF solution and can be observed before immersion only. It was because these two samples were not maintained their shape and the materials dissolved during immersion process. Figure 4.3 and Figure 4.4 showed that experimental data through EDX, the materials under study contain calcium, silicon, oxygen, and carbon, as well as trace amounts of sodium ion, magnesium ion, and chlorine ion that may have been absorbed from SPF and presented in the samples. The surface layer of amorphous calcium phosphate is generated when composite ceramides made of recently precipitated synthetic solids are submerged in simulated body fluids for 12 days at 37 degrees Celsius. Because silicate ions function as active sites in the process of new phase nucleation, the coating's density and thickness increase as the calcium silicate content of the composites rises. Magnesium ions presence in solution was involved in the inhibition of apatite formation. A negatively charged surface with a functional group, SiO, is required for the formation of apatite. The precipitation of apatite on the surface of the wollastonite coating is not significantly influenced by the rise in calcium concentration in the SPF solution. When the wollastonite coating is submerged in the SPF, the calcium ions in the coating interact with the hydrogen ion in the SPF solution to form silano in the surface layer, which raises the pH at the coating SPF and eventually produce a negatively charged surface with the functional group SiO. Figure 4.5 showed the FTIR spectra of surface layer formed on the upper sides of composite samples without immersed in SPF. And then figure 4.6 and figure 4.7 displayed FTIR spectra of Siemens after being submerged in SPS solution on days 3, 6, 9, and 12. A control Siemens D0 was examined using the spectrum. The control Siemens is used to set it apart from other Siemens that have seen apatite deposition in SPF solutions. For wollastonite plus 3% sodium alginate, the stretching vibration of PO groups were at 1008.28 cm negative 1 day 3, 1003.85 cm negative 1 day 6, and 986.92 cm negative 1 day 9, while bands in calcium phosphate showed characteristic absorption bands at 541 cm negative 1 day 3, 558.23 cm negative 1 day 6, 556 cm negative 1 day 9, and 542.20 cm negative 1 day 12. Absorption band at 1440.74 cm negative 1 day 9 and 1436.23 cm negative 1 day 12 consisted of carbonate ions. The stretching vibration of PO groups showed characteristic absorption bands for wollastonite plus 2% sodium alginate at 1009.25 cm negative 1 day 3, 1011.06 cm negative 1 day 6, and 983.61 cm negative 1 day 9, while calcium phosphate showed characteristic absorption bands at 565.97 cm negative 1 day 3, 562.91 cm negative 1 day 6, 571.08 cm negative 1 day 9, and 557.82 cm negative 1 day 12. Absorption band at 1439.75 cm negative 1 day 12 consisted of carbonate ions. As a result, the findings of infrared spectroscopy indicate the development of apatite layers on the composite scaffold through phosphate and carbonate ion peak. In conclusion, commercial wollastonite sodium alginate composite cement can be referred to as a bioactive material because it produces an apatite on its surface after being submerged in a simulated body fluid. Utilizing commercial wollastonite sodium alginate composite cement to create cement scaffold is convenient because it contains sufficient apatite to cause apatite to grow, and since SPF has been proven to be a reliable method for testing the bioactivity of materials. SEM-EDX and FTIR spectra can be used to examine the apatite formation and growth. Other than that, variations in mass and pH are other possible indication to the deposition of apatite. For recommendations, besides SEM-EDX and FTIR, X-ray diffraction HRD can be used in this future study for apatite structural characterization. Undoubtedly, a major tool for characterizing precipitated crystalline phase is HRD. These are several lists of the references. And then upon completion of this project, I would like to express my gratitude to many parties. First of all, I would like to express my thanks to Allah Subhanahu Wa Taala for His willingness to give me this chance, time and ideas for my work to complete this final year project. My heartful thanks to a dedicated and supportive supervisor Sehali Johan bin Muhammad Rizwan with all his encouragement and time that has been provided for me to complete this study, and my lecturer Dr. Siti Raihan for her guidance in this study. I would also like to thank Encik Haji Nik Muhammad Zamani bin Ismail, Encik Muhammad Zahid Ismail, and Puan Norasida Harun, which is the lab assistants, for their assistance in managing my laboratory study for this project. I would also like to thank my parents for their prayers, emotional support, and financial help to complete this report. Last but not least, I want to thank all my friends for their help in order to accomplish my objective and their encouragement as I work to fulfill my writing. Last but not least, thank you. Thank you for watching.